Hello friends, now we'll see about code optimization. Code optimization is one of the phases of the compiler which helps the compiler to build faster running code as well as lesser space occupying code. What are the principal sources of optimization? There are several reasons why we need to go for optimization. Programmer may not be aware of having these redundancies at a later stage because programmer will be writing the code in a high level language. These high level codes will be converted into low level codes, and when only then there will be some redundant codes, redundant expressions included in the low level code. So it's a must that the compiler has to do the optimization in order to get the faster running code as well as the lesser space occupying code. As you can see, this is the same quicksort program we saw in the previous video, and correspondingly we have the three address code stated as statement number 1 to statement number 30 as the three address code. Also, we have seen in the previous video the flow graphs for corresponding to the three address code. The basic blocks, we have 6 basic blocks, B1, B2, etc. up to B6, and also we have this flow graph. All these we have seen in the previous video. Now we'll proceed with the transformations that can be done on this so that we get optimized code. While doing optimization, we should keep in mind that the semantics of the code should not be changed. That is, the meaning of the code should not be changed. And that is why we need to do semantic preserving transformations or function preserving transformations. Next, we'll see what are the semantics preserving transformations we have. The first technique is local common subexpression elimination. Why is it called local common subexpression elimination? Means the common subexpressions which are present can be local. That means locally inside a block. Such common subexpressions has to be eliminated. As you can see the flow graph here, you can see block B5 having 9 instructions. This basic block B5 is taken for local common subexpression elimination. Now if you see the before part, the same basic block B5 is listed with the 9 instructions, and after doing the local common subexpression elimination, what you are getting is listed as the after section. Now if you see the block B5 with statement number 1 and statement number 3, statement number 1 is T6 is equal to 4 star I. The third instruction, T7, is also 4 star I. So we are having the common subexpression 4 star I calculated again and again. So we can optimize the code by removing the redundant code. So that's what we are doing in the after part. If you can see, we are removing the T7, the third statement. T7 is equal to 4 star I is removed from the code because it is a redundant code. Similarly, 4 star j is also calculated twice. So that code also can be eliminated. So T10 is equal to 4 star j is also removed. So likewise, whatever redundant common sub-expressions we have inside locally inside a block, that can be eliminated. So in all the blocks, wherever you find the local common sub-expressions, we can eliminate all of them. That is the first technique. The second technique is global common sub-expression elimination. If you can see, the global common sub-expression elimination is very similar to local common sub-expression elimination because it also deals with common sub-expressions, but in this case it is global. That means the common sub-expressions can be there within different blocks, not inside the same block. It can be between different blocks. Then also you can remove. But the thing is, when you are removing, you should be seeing that the value is not changed while it is coming to the next block. For example, you can see 4 star I is present in block B2 as well as block B5. In block B2 it is calculated as T2, and in block B5 it is calculated as block T6. So why we should have these two different common sub-expressions even though they are in different basic blocks? They are the common sub-expressions. We can eliminate them. But only one thing we need to understand, that when we are removing or deleting the common sub-expressions, like for example here in block B2 4 star I is computed as T2, but if T2 is not changed, okay, while it is coming to block B5, in that path if T2 is no more changed or no more modified, then we can surely delete the recalculation of 4 star I in block B5. Otherwise, if it is modified means we cannot delete. But here it is not modified, so that will be deleted. Similarly, 4 star J is calculated in block B3 and block B5, and that also can be removed. Similarly, A of T2 is calculated in block B2 and block B5, then that can be removed. So likewise, wherever across blocks you can remove, those can be removed, and without common sub-expressions the blocks can be kept. So after removing after doing the global common sub-expression elimination, we can see this is the resultant block B5 and block B6. As you can see, block B5 had 9 instructions. We did the local common sub-expressions, and after that we did global common sub-expressions, and after that we are getting this code that is having only 4 instructions in block B5. Similarly, in block B6 also a similar kind of a common sub-expression eliminations are done, and then we are getting the result after the elimination of common sub-expressions, both local as well as global. So this is the second way of optimizing the basic blocks, and basic blocks. And then we have another technique which is called a copy propagation. In copy propagation, we can take an assignment of the form U is equal to V. So this kind of copy statements can be optimized in such a way that use V for U wherever possible. After the copy statement, U is equal to V. So wherever possible we can use V for U. So you can see the basic block B5 you can see here we have X is equal to T3 and A of T2 is equal to T5 in block B5, and A of T4 equal to X. So we have to use V wherever possible after this copy statement. The first statement of block B5 is the copy statement, X is equal to T3. So in that, use V for U, that is use T3 instead of X. That's why it has been changed, like as in slide number 12 you can see the third statement of block B5 is rewritten as A of T4 is equal to T3 because we are doing the copy propagation. Then we are having the dead code elimination as the next technique. What we'll say as dead code means a variable at a particular point is said to be live if it is subsequently used again after that point, then only it is said to be live. If the variable is not used subsequently after that point, then it is considered to be dead. So such dead codes can be eliminated. An example is given if debug print. Now debug is a Boolean variable. Boolean variables can evaluate to true or false. Now suppose in various points in the program you have debug to be true, false, like that it is getting set in different places, but finally at the last assignment debug is set to false. Let us assume debug is set to false. Then whatever may be the assignments to debug previously, the last statement is going to be false. So writing if debug, that means if true, print something, that is the statement given here, that will not going to work, because always the last statement is going to be false. Debug is going to be false. Then writing a code like this after that, if debug print, the control will never go to that statement because debug will always be false. In that case, this code, if debug print, is a dead code. Such dead codes can be eliminated. So we are applying the same thing in our block B5. In block B5, previously we had this one. If you see slide number 12, you can see we have 4 instructions in basic block B5 after copy propagation. And if you can see there, x is equal to, the first instruction is x is equal to t3. And the third, and after that point, x is never used inside that basic block. Yes. So that x is not live. It is dead at that point. After that point, it is not used anywhere afterwards. So we can remove that dead code. So x is equal to t3, the first statement of basic block B5 listed in slide number 12 can be removed. And what is given in slide number 13 will be the resultant code of block B5. So block B5 had 9 instructions. We did the local common subexpression elimination, we did the global common subexpression elimination, then we did the copy propagation, then now we are doing the dead code elimination. So now it has changed into 3 statements. And the next transformation is code motion. Code motion is used for optimizing the loop statements. Loop statements are considered to be the time consuming statements because loops can run for a number of iterations. For example, if 1,000 customers are there, then if you have written some code for manipulating some data over the 1,000 customers, then 1,000 times the code will be running. So it takes lot of time of the computation. Loops can take the lot of time. So it is mandatory that we have an optimization on this looping constructs. So doing that is what we call it as the code motion. Now we can check whether there is any loop invariant computation present inside the looping statement. A loop invariant computation means if a computation is inside the loop and it is not affected by the loop inside, every time it is going to be the same. It's not going to change because of the increments. So that is what we call it as a loop invariant computation. Okay, for example, you are having I variable as 1 and inside the loop I am writing I is equal to I plus 1. That is I is getting changed into I plus 1 every time the loop goes, but that is affected by the loop. But if there is a computation which never changes, so that is what we call it as a loop invariant computation. So this kind of loop invariant computations can be brought outside the loop. For example, as you can see in slide number 14, we have a while construct. It says while I less than or equal to limit minus 2. So here this limit is a variable that is never changed by the loop, but I value is getting changed. It may be changed inside, but the limit is not getting changed. So every time this is a constant, limit is some constant, and every time the loop goes 1,000 times, if the loop goes, limit minus 2 has to be computed 1,000 times. So why we should compute 1,000 times, which is a loop invariant computation? So that can be brought outside the loop. So the same code can be changed like t is equal to limit minus 2. We can bring the limit minus 2 outside the loop, and inside the loop we can write while I less than or equal to t. So in this way we can do the optimization. So this technique is called code motion. The next technique is induction variables and reduction in strength. A variable is said to be an induction variable if there is a positive or negative constant such that each time x is assigned, its value increases by c. So if you see in that flow graph, you see there in the flow graph, you can see here in slide number 11, see block number B2, there is the first instruction says I is equal to I plus 1 and T2 is equal to 4 star I. So in this case, every time I changes to I plus 1, T2 changes by 4 star I. So this is getting, so I and T2 are related with each other. Whenever I changes, T2 is also changing. So I and T2 are induction variables. Similarly in B3 you can see J and T4. Every time J is changed, T4 is also getting changed. So J and T4 are induction variables. So these are induction variables. So whenever there is induction variable, we can remove all the induction variables but one. That means you cannot remove all the induction variables. You have to have one will be remaining, all the others you can remove. That is the meaning. So induction variables can be eliminated and to optimize the code. So you can see here this I and T2 are induction variables in block B2. So what we can do is we can instead of having T2 is equal to 4 star I, we can write like T2 is equal to T2 plus 4, because every time I increases by 1, T2 increases by 4. So what we can do is instead of making T2 dependent on I, we can bring this dependency outside the loop. Now you can see here in this flow graph, there are 3 loops. What are the 3 loops? B2 to B2 is one loop, B3 to B3 is one loop, and another loop is B2, B3, B4, B5, B2. So this is another loop. So we have 2 inner loops, that is B2 to B2 and B3 to B3, and one outer loop. The outer loop is B2, B3, B4, B5 and B2. So we can bring these loop invariant computations outside the loop so that we can optimize the code. So how it is done, it is shown here. You can see slide number 16. You can see we are bringing that 4 star J computation outside the loop, and we are changing T4 like T4 minus 4, not having us T4 as a dependent on the J variable, making it independent variable and bringing that 4 star J computation outside the loop inside block B1. Similarly, that I variable and the T2 variable are induction variables. We can make the T2 induction variable to be a non-induction variable by making T2 not dependent on I. So as you can see in slide number 17, you can see block B1 is added with another computation, that is 4 star I also is now added to block B1, and B2 is changed like T2 is equal to T2 plus 4. So in this way we can remove the induction variable. And another one is strength reduction. Strength reduction means the higher computing instructions, higher cost instructions. For example, plus and minus or least cost instructions, whereas cheaper instructions, whereas star, slash and all, or costlier instructions or expensive instructions. These instructions can be removed. So as you can see here, earlier it was 4 star I, but now we have changed it as T2 is equal to T2 plus 4. So star is changed into plus, and similarly we have changed into minus. In B3 we can see it is changed into minus. T4 is equal to T4 minus 4. So in this way we can optimize the code. Thank you.